to this course. It is called Signals and Systems. And as you can see, the objectives. Okay, we will describe signals mathematically, and you will understand how to perform mathematical operations on the signals. And then we need to classify the signals if they are continuous time or discrete time, or is the signal periodic or non-periodic, and also is the signal even or odd, and also that conjugate symmetric or anti-symmetric. And then you will also understand the impulse response. Especially we will talk about the LTI system, linear time invariant system. And we will learn the convolution and also apply the Fourier analysis that you learned in engineering mathematics to this course. And later on you will learn the filter. So that's the course objectives. And we may use the textbook. You can buy the textbook. If you don't understand some concepts, you can have this book as a reference. Prerequisite, none, but it's better that you learned linear algebra and also calculus. That'll be better for you to understand these materials here. Through this semester, we will learn this one. Okay. First, we'll learn some fundamental theories or the fundamental concepts. Once you have those concepts, mainly we will talk about the LTI system, the linear time invariant system. And through this linear time invariant systems, you will see some very good properties. And we will use that properties to manipulate the signals. So we will learn the Fourier series and Fourier transform. So far, a lot of people may think that for this course, it's kind of like a review of Fourier series and Fourier transform, or any kind of like Fourier analysis. If you have this concept and these ideas, then it will be totally wrong. We will apply that. We will apply the Fourier transform, Fourier series to the systems, and it is. I would say it is not that easy, but not that hard. But if you think it is just like doing the Fourier transform, you memorize the formula, that is totally not enough. Okay. If you just memorize the formula and use the formula, then you don't really learn anything about the signals and also the systems. How do they transform? There are so many tricks that you can use. And you'll learn that later. And then we will talk about the sampling theory. And we will talk about the Laplace transform and Z transform in the end. So first, let's just talk about the signals, because the course is called Signals and Systems. So you'll learn what signal is and also what system is. So first, let's talk about the signal. What is a signal? So what is the signal? Okay, a signal, we can think about the signal is a function of one or more variables. Okay, so a function of multiple variables. And this function can convey information on the nature of a physical phenomenon, like the sound signals, the light signals. And for the signal with one or more variables, if I have a one variable, then we have one-dimensional signals. So if we say it is like one-dimensional, that means this signal is a function This function depends on a single variable, just one variable. So the function depends on a single variable. For example, like a speech signal. So what is the speech signal? So when we talk, we have a different tone, different sounds. That is the amplitude. And this amplitude may only vary with time. So the amplitude varies with time. Then multi-dimensional signal, that will depend on, this function will depend on 2 or more variables. For example, like image. For the image, we have horizontal and vertical coordinates. So we have 2 variables. That is called multi-dimensional. So this is the function depends on 2 or more variables. So the example is an image. Because we have horizontal, the x and y coordinates. Horizontal and vertical coordinates. This is the signal. And then how about the system? What is a system? The system, you can think of the system as like a black box, or just like a box. They absorb a signal and then absorb those signal into their box, and doing something later on they create a new signal. So it is an entity that manipulates one or more signals to accomplish a function, yielding new signals. So which means if I have an input signal, then we send this input signal to a system like a box. Okay, this is the system. Then we have an output. This output we call the output signal. For example, if we have a system called an automatic speaker recognition system, then what could be the input? Because it is a speaker recognition system, so the input could be sound like a speech, a voice, right? So here we can have a speech. Okay. That is voice. And what is the system? We send a speech or voice to this system. This system we can think about like a computer, right? We send the speech to the computer. Then what do we get for the output? That I send, for example, maybe you can think about like I send the voice, and then go through this system because it's called like speaker recognition system. So the output, it may give you the name of that speaker. So the identity of the speaker. That is one of the possible output. So here the output could be the identity of the speaker. All right, another example, how about like an aircraft landing system? So this system, I can guide the aircraft or the airplane to land successfully. So what is the input signal? What input signals could be? Because it's a landing system, I need to tell the aircraft the position, the exact position that you need to land here or land in that way, right? So we need to give the desired position. This desired position of the aircraft. And then what is the system? What the system could be. I send this signal to that system, right? So I have to send the position to the airplane, right? So the system could be the aircraft. And then what is the output? So maybe like I'm flying, I know that maybe I only know that the direction that I'm going to land is in that direction, but sometimes I just fly deviately to another position. So I receive the correct signals, the positions, then I need to tune, right? I need to fine tune. So here the output could be the correction. So overall, you should know that for the systems, I receive the signals, and once I receive the signal, I manipulate that signals. By how? Depends what you want. But later on, especially for the linear time invariant systems, we have some good properties we can use. Then they give the new output signal. Next, let's just see that what is the communication system. So the communication system, I may receive the signal. We may say that this is like a message. Then this message signal, I will send it to the system. And this system is kind of like a transmitter. Okay, so because once I receive those sound or speech, maybe like in computer world, they need to digitize it to 0 and 1. Then this is like a system that change all the continuous signals into discrete. And then later on, they do something, then give the signals to another system. Then finally, they create the output signal. That's what they want. For example, if I have message signal, then they go to the transmitter. Then what is the output? Here the output will say this is the transmitted signal. So they just change the form of the message signal, the original signal, into this transmitted. And then they send this signal to a channel. Then after the channel, we have the signal called receive. The received signal. And then we send this signal to another box called receiver. And the output is, well, the estimate of the message signal. Well, here is the big system for the message signal, like the video, like the computer data, or like a speech signal. And we call those are the message signal. So for like speech signal, or like a video, or computer data. It's like a raw data. And we will send it to the system. We'll try to like convert those message signals into like something that we can use. For example, like a computer, they only recognize 0101, and so I need to convert that. So in this case, here the transmitter is to convert the message signal. Once they convert it, then they send it to like a channel, like mobile channel or like a satellite channel, so they can use. All right, so here the channel could be like a mobile channel, or the satellite channel. Okay, they do something, manipulate those signals, then it is still like digitized. So once we have the received signal, we need to send those signals to like a receiver, so they can convert it back, convert it again to like the signals we know, like the speech or the video or the computer data. So here we call the estimate of the message signal. So in this course, we will learn two types of signals. The one is continuous time, and the other one is discrete time. Okay, both are very important. Like here, you can imagine that those are continuous time signals, and then we need to convert it to the discrete time. Then we can use computer to do something, and it is still discrete time. Then I will send it to another box. Finally, I will convert it to the continuous time signals. Okay, and how do we do that? That will be at the second half of the semester. So, two types of the signals. First is discrete time signal. So what is the discrete time signal? For example, x equals n squared. And this n belongs to, so it could be from negative numbers to positive integers. Or the signal could be complex, so it's j squared. Or we can write it down. The signal is the complex exponential, e to the j 4/2 m pi. It doesn't make any sense that 4/2. We should try change that to 3/4. 4/3. Maybe. Okay, those are the discrete time signal. We also have the continuous time signal. So for the continuous time signal, for example, like 1 plus t squared, just 1 plus t, and then t is the real number. Or we can have a complex exponential, e to the jt. You can see that this t is real number, but here the n is integer, positive and negative integers. And later on, also in the second half of this semester, actually we will learn, I have a continuous time signal. Say, we can sample it. If we do the sampling, it is like a discrete signal. So if I sampled here, so I don't have values unless those certain points, then that's called discrete time signal. So here we have the notes. We have T and N. So if you see T throughout this semester, that means it is time. But time for continuous signal. Continuous time signal. So time for continuous time. So CT signal. And the N, it's time for a discrete time signal. You may also observe now that I have a brackets and also parenthesis. Okay, so if I have a parenthesis, that means it is continuous valued quantities. If I have a bracket that is discrete value quantities, why do we need to study systems? There are many reasons. Like, for example, we want to know like how to decode the encrypted signals. So like sometimes I have encrypted signals. How do I decrypt it? Which means that I want to find an inverse system. To the encoding system. Or we may want to denoise a sound system using the system like a filter design. I can denoise some like a noisy background sound. Or I can compress a sound signal. Or you want to compress sound and also transmit to a low capacity channel to save your money. Those are just couple reasons we want to study the system. And here in this course we studied linear time invariant system. So here is linear time invariant system. That means that we need to know what linear time invariant is. So what is linear? And what is invariant? Now, since we are going to talk about the linear time invariant systems, before this we need to learn some basic concepts. First is linear. So what does that mean, linearity? Linearity, that means if I have two signals, x1, x2, x1 they can produce the y1 as our output, x2 their output is y2. Then we say that the system is linear if and only if I have another signal x3. x3 it's a linear combination of x1 and x2. And then their output is also the linear combination of the output from x1 and x2. So it's a linear combination of y1 and y2. Then we say that the systems are linear. For example, if I have a signal x1 as our input, then this is the system. Then the output is y1. There. Right, and then the other two, same system, but the input is x2 and output is y2. So if the system is linear, if my input is a linear combination of our inputs x1 and x2, say alpha x1 plus beta x2, then what is our output? The output is a linear combination as well of the output from x1 and x2. So I have alpha y1 plus beta y2. So if my input is a linear combination of x1 and x2, and the output is also a linear combination of y1 and y2, then we say the system S is linear. So the system S is linear. Okay. This case, the X is like continuous, but it also applies to discrete time signal. So if I have a discrete time signal, you will see x n, and this n is in the set of the integers. So that's z. All right. Here, if you see this symbol, that means belong to or in the set. And the z is set of integer. If it is a continuous time signal, T is in a set of real number. So this is the set of real numbers. Okay, that's called the linearity. How do you verify that the system is linear? In this way. Okay. Set two signals with their corresponding output, then have a third signal that's a linear combination of the previous two, and check if the output is also a linear combination of your output from the previous signals. Next, we are going to talk about the signal power and the energy, because think about the sound. The sound can produce the work. It's like a power, or we can say that's energy. So, and also the pressure moves the eardrums, and then that also implies that the sound can have the power and energy. Here. So how do we evaluate the energy? Okay, if we want to find the energy from T1 to T2, and the T1 is less than T2, then we have the integration T1 to T2. I put the magnitude of your signal squared, and the average power between in the time interval between T1 and T2 it will be 1 divided by T1, should be T2 minus T1. This is the energy in the time period. So for the total energy, here you can see that T1 becomes minus infinity, T2 is infinity. So that's total energy. The total energy will be the energy divided by well, we just change the integrands from minus infinity to infinity. So here we have minus infinity to infinity, and the magnitude of your signal squared. Well, what is the power? Suppose it's from minus t to t. So we will think of this, and that the denominator goes to infinity. So 1 over 2t minus t to t. And with that, t goes to infinity. That will be your power. And this is for continuous time system. Well, for the discrete time system, similarly, let's write it down here. Similar for DT system. How do we have or define the total energy? The total energy will be the summation n from minus infinity to infinity, and the magnitude of the signal squared. And then power, there'll be 1 over 2n plus 1, and have the summation n from minus n to capital N x. And with that, n goes to infinity. Okay, you can try to find the energy, the total energy and the power. In this case, okay, if you plug in, I'll give you 3 minutes. Try to find the total energy here. So the total energy should be infinity, right? How about the power? So the power is also infinity, right? How about the discrete time case? Let's just find it out the total energy. Okay, so if to get the total energy, you'll get alpha to the 2n, and you can continue at home. Okay. All right, if you don't have any questions now, let's see some very important concept about the variables. We will also use that later. So first, with a signal, what is the time shift? What does that mean, time shift? If I have a signal, if I shift t naught, t minus t naught, what does that mean, t minus t naught? Shift to where? Shift to the left or shift to the right? Right. So I will shift to the right by t naught. Then, okay. So if I shift Here we can say that T naught is here. Or or this is like T naught. So if I shift T naught to the right, then you see that signal, the shape of the signal is the same, but I just shift to the right. Time reverse. What does it mean, time reverse? If I have a signal like this, right? So if my signal is, say, like Nike, all right? Then what is the time reverse signal? X of minus t. So minus t here, it means that I flip according to the y-axis. So I flip. So this one I flip, then I should get the inverse of Nike, like that. Next, time scaling. So if my signal is like an rectangular pulse, but not a rectangular pulse, just have 0 between -1 and 1, but 1 outside that region. So here is -1 and 1. So what is x of at? Rather than t, now I have at. So it's kind of like changing variables. Now it becomes at. So it's either compressed or become widened. So here, I only need to change this part, the value here. So anyone could know what is the value. 1 over a? 1 over a once, 1 over a twice, 1 over a, correct. So we have 1 over a, and here will be -1 over a. So that's why you can see that when a equals is greater than 1, say -1 over 5 or 1 over 10, so it compresses. So if we compress it, becomes like a narrow. If you don't have any questions, now I have an example. You can see that my signal is either sine function or 0. We can express here in this way, or we can express in a Heaviside function. How do we do this? If we express that in Heaviside function, let me ask another way to express this expression. Using Heaviside function. Hold on. So it's equal. This is equal to sine 2 pi 440 t. Then, okay, u of t minus u of t minus 1. Perfect. Right. So I can express this signal in 2 ways. This is the unit step function. I think we will also mention that later. Okay, so if first let's plot this function, this signal. Here's y. That's t. It's from 0 to 1. So suppose this is 0 and 1. Then the sinusoidal function, when t equals 1, that will be 2 pi 440. So it's 2 pi theta is still 0. So here we should have. So if I shift 1, y over t minus 1. So how does this figure look like? If I shift 1, that means I will shift this signal to the right or to the left. I'll shift this signal to the right by 1 unit. So I will shift 1 unit. So you will see this from 1 to 2. Okay. So here is 1 and 2. Another example, if I have a signal with different frequency, 440, 880, and 1760. This signal looks like, first is 440. Well, suppose here. And now it becomes 880, so it compressed. And then 1760, so it compressed. Okay, so here is 1760 hertz, and this is 880 hertz, and 440. So in this case, what is the y inverse? Y of minus t. If we do the time reverse, if we have time reverse, this should be y of minus t. Then we have minus 1, minus 2, and minus 3. First, that's 440 and 880 and 1760. Okay, any questions for this? All right, if you don't have any questions, next, very important, if I have a signal, we say this signal is like a triangle signal, like this. Now I want to do shifting and also scaling. So if I have shifting and scaling, which one should I do first? Shifting first or scaling first? Two ways. Okay, first, let's see. We can rewrite this signal into, we just take alpha outside, the factor outside. Then we have t plus beta divided by alpha. So this means now I shift. I have like new 0. Okay, my 0 is at minus beta over alpha. Then I scaled by alpha. Okay, so in this case, you can like changing variables. This is like x over alpha. Let's see another symbol, t double prime. Now change the variable. So the origin, the 0 becomes minus alpha, minus beta over alpha. Okay. So here, t is equal to minus beta over alpha. That is our new 0. And then scaled by alpha. So in this case, let's find the new 0 first. The new 0 is minus beta over alpha. And then scaled by alpha. If I scale by alpha, this one here, the width will become 1 over alpha, right? Here, 1 over a. Okay? So now this width, this will become like 1 over alpha minus 1 over alpha. Okay, the width will be 1 over alpha. So here, the width will be 1 over alpha, right? Again, x over alpha t. In this case, it's 1 over alpha minus 1 over alpha, right? Okay, This length will be 1 over alpha. So here we should have 1 over alpha because this is our new, kind of like a new 0. I shift this one plus, so I shift to the left and then scaled, compressed, kind of like compressed if alpha is greater than 1. So here we have, this becomes 1 over alpha. So here we have minus beta over alpha plus 1 over alpha. In this case, we said this is like I do the compress. We compress the alpha first and then we shift. Right? It's like I compress the alpha, so 1 over alpha, this is 1 over alpha, 1 over alpha, and then I shift to the left. So I shift this to the left. This is kind of like my new 0. So the first way you can do that is to compress, then shift. You can also shift first, then compress. So if I shift first, if I shift beta first, then we get, this is minus beta plus 1, minus beta minus 1. Then we compress by alpha. So here I compress by alpha. Again, this will be like divide by alpha, right? Similarly, it's just like this. If I compress by alpha, I divide by alpha. Okay, so I divide by alpha overall. Copy. And then here we have minus beta minus 1. Divide by alpha. Minus beta plus 1. Divide by alpha. Oh, I also need to divide by alpha here. You have similar results. So no matter that you do the compression first or you shift first, you will get the same result. Now next, let's talk about the signals. For even signals or odd signals, how do you know that it is an even or odd? So here we need to define what is an even signal, what is an odd signal. We say that signal is odd if and only if the original signal and the reverse signal, they have a different sign. Okay, so here we have like a minus sign here. If it is an even signal, when the original signal and the reverse signal are the same. For example, okay, this signal minus 1, 1. Is this even or odd? Which one? Also, how about this signal and this signal? Okay, so first, this signal is even or odd. Okay, if you say even, then I just put even. How about the second one? Odd. Suppose you are right. We say odd. Then how about this one? Correct, that's neither. It's not either even or odd. But here's a note. Every signal can be written as a sum of an even signal and an odd signal. That means this is not the even signal or odd signals, but every signal can be written as a sum of even and odd signals. So why? First why? Let's do the proof. And then we'll try to figure out how do we express these signals as a sum of even and odd signals. So the signal is, suppose the signal is x of t. And I can rewrite the signal as x of t plus x of minus t. I do the reverse over 2. Okay, plus, they said that even and odd, so plus x over x of t minus x of minus t over 2. Right? They cancel out. And then here it is x of t. Okay? And this is even. And this is odd. So in this case, let's talk about this signal. Okay, we can find the even signal and also the odd signal. The signal is from -1 to 1 and -1 to from -1 to 0, and here also from -1 to 0. This is -1, here 1, -1, and 1. So we need to find the even part, and also the odd part. So the even part we know that should be 2 x of t plus x of minus t divided by 2. So since we know the even signal is xt plus the reverse signal divided by 2, so we can plot xt, the signal, and the reverse signal. So the original signal so it could be this is equal to x of t plus, okay, doing the reverse, they don't have that a function, so we need to plot our reverse signal. So what is the reverse signal? We have blue one and the pink one here. That's 1, 1, -1, and 1. Okay, this divide by 2. Then you'll get the signal like here. -1, 1, and here is 1 over 2. -1 over 2. And for the odd signal, that'll be x over t minus the reverse signal. So the good thing is that they just copy it here and then do the minus Similarly, divide by 2. Then you have this is 1, and here 1/2 minus 1. Minus 1, this is minus 1/2, here's 1. Okay? So, the original signal can be not divided into these two, but can be the combination of these two signals. Okay? The even plus odd, they will give you here. Another concept or ideas that we have to know before we really talk about the systems is the periodicity. So we will define that the signal is periodic or no. What is the periodic? We say that the continuous time signal is periodic. That means if we exist a t, this t is greater than 0. And then we call the period, this is like a period, such that if I shift by t, if I shift by this t, the shape is still the same as my original signal. Then we say that this signal is periodic. So here's a note. There could be many t that satisfy, because you can think of this t as like 2t, 4t, 3t, what else? Just change these variables. As long as they shift by the period, they still have the same shape, then this signal is periodic. Since we have so many t that satisfied that equation, we have the fundamental period t naught. We call this fundamental period t naught is the smallest of all periods of x. For example, like x, cosine t plus 2 pi, cosine t plus 4 pi, plus 8 pi, plus 16 pi, they are still equal to cosine t, right? In this case, 2 pi is the smallest period, so we call that fundamental period. That's 2 pi. So if we plot the cosine, we will have, here will be 2 pi. Then our fundamental period t naught is 2 pi. This is 2 pi, right? And let me see. Here's 4 pi. Okay. You can also say that the period is 4 pi. So like here, and then every 4 pi, they have the same shape, but it is not the smallest period. The smallest one is 2 pi. So you can see that if I shift by 2 pi, you still get the same shape. If you shift by 4 pi, you still get the same shape. But the fundamental one is the smallest one. This is the case for continuous time signal. How about the discrete time signal? Let's see. We also have a definition for the discrete time signal. We say that the signal is periodic if we exist in capital N that's greater than 0. Then the period is that if I shift by n, I get the same shape or the same signal again. And this n is an integer. Okay, be careful, that's the integer here is the real number. So this is integer. Integer means that 1, 2, 3, 4, 5, minus 1, minus 2, minus 3. Okay, then the smallest periodic n naught is called the fundamental period. Okay, so now we just learned that in continuous case, cosine t is periodic. How about discrete time case? Cosine n, remember this n, well, it is discrete. So if I want to, well, first let me ask you, this is periodic or not? Every time if you don't know that, we just check the definition, okay? As long as we can find that this equation holds, then it is periodic. Okay, so if it is periodic, that means cosine n plus capital N is cosine n for all lower n, case n. And remember that this holds when this capital N is integer. Okay, if it is not integer, then, well, from the definition, it only says that the n should be integer. So if this n is a multiple of, say, 2 pi, what happens? So if n is a multiple of 2 pi, then we say cosine n plus capital N is cosine n. Right? Because we know cosine here, cosine t plus 2 pi, that will be cosine t. Similarly, that we can apply that to the discrete case. We need m plus like 2 pi n. But however, this is impossible because n should be an integer. If I times like 2 pi, no way. Right. So here, but this is impossible because the capital N, this n should be integer. So cosine n in discrete case, that is not periodic. How about cosine 2 pi n? Is that periodic or not? In this case, this is periodic. Now the next, we also need to talk about the signals with complex numbers, like a complex exponential. We will also use that later. So what is the complex exponential? If I have a signal, that's c times e to the at. This constant c and a, or we say the parameters, are complex numbers. For example, e to the jt, or x is e to the 1 plus 5jt, or the c could be the complex number. So let's see, 1 plus 3j e to the jt. Then we can use the Euler's identity. E to the j theta equals cosine theta plus j sine theta, the Euler formula. So using the Euler formula, the x is equal to, suppose, for example, e to the jt, then we can divide it into 2 parts. The real part, cosine t, and the imaginary part, j sine t. And here, the e to the jt, it is periodic. And what is the fundamental period? The fundamental period should be how much? You can see here. We have a cosine, sine. So what is the fundamental period? 2 pi, right? So this is for any real number, omega naught. So for omega naught, then how about e to the j omega naught t? What is the fundamental period? We know this is periodic. And since it is periodic, then we are interested in knowing that what is the fundamental period. So this is periodic with fundamental period 2 pi over omega naught. Correct. But not all complex exponential are periodic. Okay, for example, if I have a signal that's e to the minus 1 plus jt. Here you can see that we have e to the minus t times e to the jt. So this part make it non-periodic. So we have e to the minus t, and here cosine t plus j sine t. It is not periodic because you can see, you can also plot. The signal looks like this one. Whatever you shift, it cannot just match to your original signal. And then we can also express cosine t or sine t here, cosine omega t or sine omega t, using the complex exponential. Cosine omega t is the real part. This is the real part of e to the j omega t. And sine is the imaginary part. So cosine will be e to the j omega t plus the e to the minus j omega t divided by 2. Then sine omega t is here. Okay, that's the using complex exponential to express sinusoidal functions. Why? Why are complex exponentials so important? Because in the LTI system, what input we have going through the LTI system, then you'll get a similar output, which means that if I have input c times e to the at, okay, they go to the LTI system. If it is complex exponential, you will see that the output, you will still see the same shape, c e to the at, but you have another constant k. And this k depends on the value of a. Later on, but not this week, maybe next week or in the third week, we will see that. Similarly, for the discrete time exponentials, if we have the input c times a to the n, then we send it to the LTI system, you still get c times a to the n, but now as you scale it, we have a k here. And here we have our general form for a discrete time complex exponential. Our signal is c times a to the n, and the ca, these two are complex numbers. For example, like 5 times j times 3 to the n. So the c is 5j, a is 3. Or it is 1 plus 3j times 1 minus 4j to the n. We can also write the complex number into like a polar coordinate. So the c could be the magnitude times the phase. Magnitude times the phase. In this case, then your signal xn is the magnitude times the phase. Then we have a question. Is the discrete time complex exponential e to the j omega naught n periodic or not? For discrete time case, then you need to check here, right? So if you check, what do you get? So let's see. We know that e to the j omega naught t, it is periodic, and the fundamental period is 2 pi over the magnitude of omega naught. Now, considering the discrete time case, we want to find the capital N, that's the integers, such that this equation holds. So first, e to the j omega naught m plus capital N. This should be equal to e to the j omega naught n. Then we can say that they are periodic. But let's check this. This one, e to the j omega naught lowercase n times e to the j omega naught capital N. That's equal to the right hand side. What does that mean? E to the j omega naught capital N should be 1. Okay? If this should be 1, that means omega naught capital N is a multiple of 2 pi. For this to be true. Well, if you have a complex number, say this one, we have b and a, this is theta, and the magnitude is m. So a plus jb will be the magnitude and the phase. So if I have just j, that means the magnitude is 1, and the phase is pi over 2. This is equal to j 5 pi over 2, and so on. Okay, so here it should be like every 2 pi. So that's why when n is the integer, okay, then omega naught capital N should be a multiple of 2 pi to make sure that they are periodic. And we say that omega naught n is a multiple of 2 pi if and only if the omega naught capital N is 2 pi k for some integer k. So omega naught over 2 pi is equal to k over capital N. That means this is periodic if and only if omega naught over 2 pi is a rational number. The rational number, that means a ratio of two integers. Therefore, e to the jn, e to the jn is not periodic. But e to the j 1 over 2 pi over 2, and this is periodic. Okay, then we can find the fundamental period. Okay, so for the fundamental period here, so the fundamental period, the n naught should be 2 pi k over the magnitude of omega naught. And then k is the smallest integer. I need the k to make this an integer. Okay. For example, e to the j 2 pi over 3, and what is the fundamental period? The fundamental period should be 2 pi over 3 divided by what? Two pi. You get 1/3. So the n naught is 2 pi k over 2 pi over 3. And this is 3k. So k should be the smallest integer to make that this ratio, the fraction is an integer. So we can choose, we chose k equals 1. Then the fundamental period is 3. And how about e to the j 3 pi over 4? And okay, let's find your fundamental period. And you can also tell me that the value of, what is the value of k? We need omega naught over 2 pi is a rational number. So first we can divide by 2 pi. That's 3 over 8, right? Now, for the n naught, we need 2 pi k over omega naught. That's 2 pi k divided by 3 pi over 4. So that is 8 over 3 times k. Right, so now what is the fundamental period n naught and what is k? We need to find the k to make 8k over 3 integer. So how much? The fundamental period n naught should be 8, right? Because I can choose k equals 3.